All right, welcome back, and let's continue. So we've talked about name node, data node, and secondary name node. We've talked about how we split files into blocks. And okay, so blocks are stored in data node, but what if the data node failed? I mean, commodity hardware fails more frequently than those hardware for name node, right? So how do we define a fail of data node, or how does a name node judge if a data node has failed? So basically, if the name node hadn't heard from a data node for 10 minutes, that is the default value, the data node is considered dead. So remember, the data node send a heartbeat to name node every 3 seconds. So 10 minutes is relatively a large time interval compared to 3 seconds. Okay, if we use a single PC, if it fails, you lose all your data. Now in HDFS, if we only store one copy of the block in some data node, then when the data node fails, you lose that block, because the content of the block only stores in data node, right? A name node cannot help here. All right. So HDFS guarantees data reliability by generating multiple replications of data, or say multiple copies of data. So basically, each block has 3 replications by default. You can adjust this number, and we will also discuss why the default value is 3 here later in today's lecture. Okay, the replications will be stored on different data nodes for sure. I mean, if you store all the replications in one data node, then when the data node is fail, I mean, you're still gonna lose all your blocks, right? So the purpose of storing replications is when the blocks were lost due to the failure of a data node, they can be recovered from other replications. So the idea is, okay, the name node has all the information about this block except its content. Okay, so basically the name node will detect that a data node is failed. So it will have a list of the blocks that stored on that failed data node, and it also has the information like where the replications of these lost blocks on other data nodes. I mean, then the name node can use this information to recover the lost blocks from the other replications on other data nodes. So that's basically the idea. Okay, the problem of this replication thing is, okay, if each block has 3 replications, then the total consumed space is 3 times the data size. So basically, the X here, if each block has X replications, then you would have X times the data size of your total consumed space. So this replication thing also helps to maintain the data integrity. So data integrity is whether the data stored in my HDFS are correct or not. The idea is HDFS would consistently check the integrity of data stored in the data nodes by using the checksum. All right, so once it finds a fault, means some data or some block is corrupted, then it reports the name node about which block is corrupted. All right, so the name node would create additional new replicates and therefore create the new replicates from the replications and delete the corrupt copies. So in such way, the data integrity has been maintained. So let's see this example of how the replication are managed. So where to store these replications. So the whole idea of replicates 3 times and stored on different data nodes is that, okay, whenever one data node fails, we can recover the data from other data nodes. For example, we have 5 blocks here. We store them in 4 different data nodes, and as you can see, each block would have 3 replicates. So whenever one data node fails, for example, the data node 1 fails, then we still have block 1 in node 3 and 4. We have block 2 here. We have block 3 and block 4. And we have 2 replicates of each block that is lost because of the failure of data node 1. Then we can store we store these blocks maybe when the data node 1 is online again, or we can initialize not initialize, but we can find a new place, let's say a data node 6, for example, and put blocks 1, 2, 3, 4 in the new in that data node to keep, to maintain that there are always 3 blocks, 3 replicates for each block in the HDF. Okay, now the problem comes, why 3? Why not 1? Well, why not 1 is quite clear. If there is only 1 replicate, whenever the data node fails, the block is lost, and there's no way that you can recover it. So why 3 is enough? Alright, so here let's do some math or do some computation of probabilities. Alright, so let's assume that the number of node is 4,000, is n here. The number of blocks are equals to 1 million. So basically, you have so for one node, there are R over n equals to 250 blocks per one node, right? And the node failure rate, FPD, equals to 1 per day, means you expect to see 1 machine failed every day. Alright, so if 1 machine fails, then all the blocks in that machine, in that node, are lost. So the number would be R over n, as we computed here. Since the expectation of failed machine in 1 day is 1, so the expectation of number of losing blocks in 1 day is 250. Now, let the number of losing blocks follows Poisson distribution. If you're not familiar with if you are not familiar with Poisson distribution, it is a discrete probability distribution that expresses the probability of a given number of events occur in a fixed interval of time if these events occur with a known constant mean rate and independently at the time since the last event. So basically, the Poisson distribution models the event, the number of events occurring in an interval of time So for example here, the number of losing blocks is the number, okay, the losing blocks is the event. Okay, the number of losing blocks are the number of events. In one day is the interval of time. So the Poisson distribution actually models this kind of thing, and all it needs, if we look at the CDF of Poisson distribution, where we have probability of x equals to k is lambda to the power of k times e to the power of minus lambda and divided by the factorial of k. So k is the number of events, and lambda here is the mean rate. For example, in our case, the mean rate lambda is 250 here. So this is the expectation of number of losing blocks in one day. So this is the interval of time. The interval of time is the same here. So we want to know the probability of this number of losing blocks in one day. That's the number is larger or equals to 250. We are actually going to compute the CDF of Poisson distribution. But anyway, I mean, you can find tools online to do the computation, and we just skip to the result here. So it's around 50%, 51%. Okay, so what does this mean? It means that if the number of replication is 1, then the probability of losing more than 250 blocks in one day, the probability is 51%. So more than half. So that is to show you that if we set replication factor equals to 1, that will be a problem. All right. So let's see the case of 3. So again, the number of nodes equals to 4,000, and the number of block replicates is equals to 1 million times 3, because we have 1 million blocks, and each of them have 3 replicates, so it's 3 million. All right. We also assume the capacity of each node is 4,000 gigabytes. Okay, we use GB here to represent the capacity of each node. We have the node failure rate, which we have introduced before, still 1 per day. Okay, replication speed. Here, the replication speed is the bandwidth for replication. For example, if the block size is if the block size is 128 MB divided by this replication speed, we would have like means we need around 95 seconds to do the replication, to restore the data. And here, I mean, we have ignored the communication time on the internet. Like we the data node sends the information to the data. The name node sends the information to the data node, and so on and so forth. All right. So in this case, if one node fails, then there would be R divided by N, which equals to we have done the math before. Now it's equals to 750 replicates or blocks that are unavailable. All right. We also noted this as B. So, all right. So now we have N nodes in total, where one of them is failed. So we still have N minus 1 nodes that are alive. And we have B replicates in that one node. And for each block, for each block of this B blocks or replicates, there are 2 replicates of that block on the other data nodes, which means on this N minus 1 data nodes. So we have a 2B block on N minus 1 other nodes. So that means there are on average S equals to 2B divided by N minus 1 equals to 0.38 replicates per node for the blocks in the failed node. All right, so we're good here. So if the second node fails, then 0.38 blocks now have only one single replica. Now let's consider the third node. Okay, so if the third node fails, so if there exists a particular block that have 3 replications where 2 of them are already on that 2 nodes that fails, so the probability that the third node has the only remaining replicates of a particular block here, because we have N minus 2 nodes still alive, and that block is 1, so it's 1 over N minus 2. This is a probability, which is this, the number is here. Okay, so the probability that it has none of these replicates is 1 minus the probability of it has the remaining, the last replica of a particular block, and to the power of S. Recall that S is the number of replicas per node for the blocks in the first failed node. So in other words, S is the number of replicas that it has 2 replicas on the 2 failed nodes. All right, so that's why here to the power of S. Then the probability of losing the last replica of a block is 1 minus the probability of none of this. It has none of these replicas, which equals to this number. Here maybe a little bit confusion, so I want to point out that in the first probability here, we're talking about a particular block. And here is a block, which means a general block. So the idea is we first consider that for a particular block, where the block has for this particular block, it's the 3 replicas has 2 of them are on those 2 dead nodes. All right, and then we compute that it has none of those replica, which means it's 1 minus probability of last to the power of s, and then we have the probability of losing the last replica of a block. I mean, in general, any block. So this is the probability that we have computed here. All right, so now assume that the node failures follows the Poisson distribution, which we have discussed before. So the rate is, so FPD is the failure per day divided by 24 hours times 3,600 seconds. So we have 1.15 times 10 to the power of minus 5 per second. This omega is the failure rate, okay, of a node in a second. Now the replication is a fully parallel operation on the remaining nodes. Okay, so here this assumption is just to make the computation here or the model here to be easier for understand, because in the real case it may not be fully paralleled, but let's take it as a fully parallel operation for now. And so the recovery time here, GB, is the capacity of a single node, but in gigabytes. So we times it with 100 here, divided by MPS is the bandwidth reserved for replication, or see MPS here is, yeah, so this is MPS, sorry, it's the replication speed, okay? And we have n-1 other nodes, so we do it parallelly, which gives us 740 seconds to recover one node, right? So the recovery rate noted as mu is equals to 1 over the recovery time. So we have it here. Then the expectation of number of failed nodes in 1 second would be omega over mu equals to this number. So here basically you can understand this expectation in this way. So basically this is let's say this is this is 1 day. Okay, this interval is 1 day, means 24 times 3,600 seconds. We know that there will be one failure happens in this 1 day, and once the failure happens, we need to recover it. So the recover time is 740 seconds. Then if we randomly take 1 second, from in this interval, when this second falls into during the recover interval, then it's a failed nodes. There is a failed nodes here. But if the second we take is outside the recovery time, then there is no failed nodes. So you use this 740 divided by here, the total time in 1 day, which is 1 over omega divided by 1 over mu, which is is 1 over mu divided by 1 over omega, which is omega divided by mu. Omega divided by mu. All right. So this is the expectation of number of failed nodes in 1 second. Now, at any second, we know that the probability of there exist k failed nodes follows the Poisson distribution. All right. So again, I mean, the failed nodes means the node is failed and has not been recovered yet. Okay. Then we can compute the probability here. The probability of 0 failed nodes is 0.99. For 1 failed node, we have this number. So for 2 or more failed nodes, we use 1 minus this part and minus this part again. We have this number. So this is the probability of we have 2 or more failed nodes. Remember here, when we already have 2 or more failed nodes, and the third failure, let's say we have 2 failed nodes, okay? The third failure, when it happens, there is no way that you can recover the block if the block happens, if all the replicates of that block happens to distribute it on these 3 failed nodes. So for the third failure, we do not need to consider the recovery, which leads us to this here. The rate is like this. So basically, we use the probability of having 2 or more failed nodes, and times omega is the failure rate of the third one. Here we don't consider the recovery, and we have this number. All right. Here the assumption is the failure of the third node has nothing to do with all the other nodes. So all the nodes are failure. Yeah, including we are using Poisson distribution here. The hidden assumption is the failure of the nodes are totally independent. Okay, again, this is may not be true because we have RAC. Yeah, I've talked about RAC. So basically, it is possible that due to, for example, the outage of power, all the machines or all the nodes on a rack would be offline at the same time. But again, here we just simplify the model, simplify the problem. Assume that the failure of all the nodes are totally independent. We have this rate of third failure. Okay, so then this times the probability of loss. Again, so just to recall, the probability of loss is actually means the probability of losing the last replica of a block when you have, yeah. Now, so basically the rate of losing a data block is lambda here equals to this number. All right. Now here in this slide, we only need to use lambda here. So according to exponential distribution, so the exponential distribution is the probability distribution of the time between events in a Poisson point process. So basically, it models. Okay, so for example, this is 1 year, and so it it models that the probability of losing a block in that 1 year. Okay, if we compute the PDF and the lambda is this lambda here, t is 1 year, so t is equals to this because the lambda is per second, so that t should be second as well. And now we have the probability here, and this is a really small number. All right, so that shows that the replication factor equals to 3 is good enough. Well, so it took us a lot to here. There are some I mean, if you are not familiar with Poisson distribution or exponential distribution, you should learn it by yourself using Wikipedia. I think Wikipedia should be enough for the slides here. Yeah. So this is so here we use a simplified model to show that the replication factor equals to 3 would make the probability of losing a block even in 1 year. The probability is much less than 1 and pretty close to 0, basically. So that is good enough. And we called simultaneously failure. So basically, if one node fails, we've lost b replicates. Okay, b is the number of blocks on one node. Okay, so if 2 nodes fail at the same time, then we lost some second replicates and more first replicates. So basically, the idea is this is the blocks in one node, and let me see. Yeah, so this is the block in the other node, and here is those replicates that both replicates are lies in both nodes. And yeah, so this part here and here is for those we only lost the first replicates. Okay. And if 3 nodes fail, well, you can see it's pretty clear that, well, you are going to lose some third replicates, some second replicates, and some first replicates. So that is basically the idea of simultaneously failure. And let's try to model this. So assume that there are n nodes and k of them have failed simultaneously. So we define the L1 kn is the number of blocks that have lost 1 replica, and L2 is the blocks that have lost 2 replicas, and L3 is to lost all 3 replicas. All right, and recall the B is the number of unavoidable blocks in one node if one node fails, or the number of blocks in one node. Okay, so when k equals to 0 means no node have failed, everything equals to 0. When k equals to 1, L1 equals to B, because one node fail, you would have lost B blocks. For B blocks, you have lost 1 replica. Okay, and for L2 and L3, the number is 0 as well. Still, I mean, okay, k equals to 2. Let's start from L2 first. The idea here is pretty similar to what we have we have mentioned before. So basically, L1 1n is the number of blocks that have lost 1 replica before when k equals to 1. So for all of them, they have another 2 replicates lies on different nodes. And how many nodes in total? N minus 1 nodes. So that's 2 and minus 1, the meaning of 2 and minus 1 here. So basically the expected number of blocks that have lost the 2 replicates would be 2 times L1 of 1n divided by n minus 1. All right, so if we have this number, then the number of L1 to n is easy to get. I mean, if we draw the Venn graph again, so this is okay, so this part is L2 to n, sorry, to n, and okay, each of this circle, this is B, and this is B as well. So basically you have 2b minus sorry, here should be 2 times, because okay, so L2 to n is the blocks that have lost 2 replicates. So the total replicates should be 2 times L2. So you use B plus B minus 2 times L2. That is L1 of when k equals to 2. When k equals to 3, let's first look at L3 here. So the idea is quite similar to where we get L2 of 2n. That is, we have L2 2n, this much blocks that have lost 2 replicates, and they have the third one somewhere in this n minus 2 nodes. So the expectation of L3 would be L2 of k equals to 2 divided by n minus 2. And for L2 here, this part is clear. We have mentioned that before. You can take them as the new blocks that have lost 2 replicates. So we need to plus the old blocks that have lost 2 replicates, and minus those have lost 3 replicates, because this part, the L3 comes from L2. Right? So L2 minus L3 is those old blocks that have lost 2 replicates, but have not lost the third one when a new node, the third node fails. So that's how you get L2 here, and L1 here is similar. So you've now got 3b, right? Because you have one more node, and you minus 2 times L2 minus 3 times L3. So that's basically the idea. So if we extend this to the general case, this is the formula. So basically, I think everything is just the same as before, except we need a couple more words on this. So basically, the L3, you do the L2 first, and you remember to add the old blocks that have lost 3 replicates. So again, this part is new, and this part is old. You just remember add the old one. And for L2, we have explained this before, so we don't do it again. And for L1 as well. So if we do the recursively computation here, let n equals to 4,000 and b equals to 350. Those numbers are what we used before. So here's what we have. All right, when 15 nodes failed, the expected, okay, so here should be the expected. All right, so expected number of all 3 replicates lost. The expected number of blocks would be only 2, while the expected number of blocks that loses 2 replicates would be more than 400, and not mention the first one. So the idea is basically when you have 3 replications for each block, 50 nodes failed, you would only lost 2 blocks. Even 200 nodes failed, you would only lose 76 blocks. But if you only use 2, okay, here the number is not accurate. I'm not sure if you can identify the problem here or not, but I will leave that for your homework. But in general, you would have something similar to this number. So basically, you would have nearly 3,000 blocks that lost 2 replicates. If you set the replication factor to 2, then the block is totally lost. Okay, the number is around 3,000 if the failed nodes is 200. So basically, that also shows that the replication factor set to 3 is strong enough for us to preserve the fault tolerance. Okay. All right. So if the replication factor is 3, as we have mentioned a long time before, we have a rack here. So recall that the nodes in one rack, they are supposed to be physically close to each other. So the reason we have this rack awareness algorithm here is try to preserve the data from being lost. In the meanwhile, increase the speed of write and read and recovery. Okay, so this is because the speed between nodes in one rack, the speed is fast, and the speed between the speed of transportation between nodes from different racks would be, the speed is low. Here the speed is high. So basically the idea of rack awareness algorithm, when the replication factor is 3, we put the first replica on the local data node. The local data node means the data node that is same as the client. Okay, if say the client is not a data node, then this this data node would be randomly picked based on the distance. We will introduce distance later, but based on the distance between the data node and the client. All right, so the second one would be on a different rack from the first. And the third one would be on the same rack as the second, but on a different node. For example, block 1, so the first replica is stored here on rack 1. So the second and the third cannot be stored in rack 1, in any node in rack 1. So it's stored on rack 2, but and both of them are stored on the node that is in the same rack. So you can see the same pattern for block 2, for example, here and here. For block 3, we have the first one here, second and third here. and for block 4 and 5. All right, so the reason that we use this rack awareness is to reduce the latency between of write and read while maintaining the fault tolerance. So the latency here is, the idea is the speed between so the speed of between different blocks in one node, the distance or the speed is the highest, the distance is the smallest, is 0. The distance between two nodes in one rack is a little bit higher, and the distance between two nodes in different racks is even higher. And okay, if the nodes are in different data center, the distance is higher again, means the time is the largest. So for writing, as we will introduce later, write is in the blocks are write in a pipeline. So basically, we reduce the number of involved racks from 3 to 2 in order to reduce the total time of writing. For reading, we do want blocks from read blocks from different racks so they can do parallelly. So yeah, it is so 2 racks involved is definitely better than 1. That is only for reduced latency, but if we consider the fault tolerance, so the basic idea is to never put your eggs in the same basket. So put them in 2 different racks would be it would be safer, and we don't have to worry about the data even if the entire rack fails, for example, because of the power failure. The power failure, because we would still have one replica stored in a different rack, so that would be safer. All right, now let's look at the write and read operations in HDFS. So for write in HDFS, there are 3 steps: create file, and write the file, and close the file. Well, here you can see the name node we have already talked about it, and several data nodes. And you have a client here. So here, the distributed file system and the FS data output stream, these 2 are 2 instances of the Java class of Hadoop. So although both of them play essential roles in the writing operation in HDFS, we're not going to dive into the implementation details of these 2 classes. So if you are interested, you can refer to the API of Hadoop. But here we will just briefly introduce what they're doing. Okay, so as the first step, the client calls the create function on a distributed file system. So basically, the client tells the distributed file system that I want to create a file, and the distributed file system will then tell the name node that, well, someone want to create a new file in the file system, and I need you to assign some blocks for me so I can write them in. Then the name node would perform a set of checks to make sure that the file does not already exist in the file system, and the client has the right permissions to create the file. So if all these checks pass, the name node would make a record of the new file and tell the distributed file system. Then the distributed file system will create a FS data output stream for the client to start writing the data to. So here is the create file step. So the client starts to write data. So basically, the FS data out stream will split the data into packets, right? And write this packet to a data queue, which contain 3 data nodes. So these 3 data nodes forms a pipeline. So basically, the data will come to the first data node, and the first data node stores each packet and pass it to the next one, and so on. And when each data node finish the writing, it will send an egg package back, and this one is also passed through data nodes, and eventually goes to FS data output stream. So this is the procedure of write file. So as the final step, when the client has finished the writing data, it will tell the stream that the writing is done, and also the distributed file system would tell the name node that this whole procedure has complete. So that is basically the write operation in HDFS. So there are some additional points that I want to mention here about the write procedure. So first of all, there's only a single writer allowed at any time to a specific file. Okay, so basically, if there are multiple clients, let's say there has already been a client that opens a file for writing, and name node has known that, and here comes the other client wants to write into the same file and ask for the permission from the name node. In this case, the name node will reject the write request from the second client until the first client has finished writing. All right. The second point is the blocks are writing simultaneously. So if a file contains multiple blocks, they are writing simultaneously. But for one block, the replications are replicating sequentially, as you have seen in this figure. So basically, the data passes from the first data node to the second and to the third. So the replicating is sequentially. And the choice of data nodes is random, based on replication management policy and record awareness, which we have mentioned before. So this is right in HDFS. Now let's look at the read in HDFS, which is simpler. So again, we have name node and data nodes and a client here. We also have a distributed file system and FS data input stream. So this is read, so it's an input stream. And again, this distributed file system and FS data input stream are 2 instances of the corresponding classes in HDFS. So basically, the client opens the file it wishes to read by calling the open function on the file system object. And the distributed file system would tell the name node that, okay, there's a client who wants to read a file. And the name node would give the block locations back to the distributed file system. Then the client starts to read the blocks through the FS data input stream. and when the read is finished, the client will tell the FS data input stream that the read is finished, so call the close function, and that's the end of the read in HDFS. So there are also several points I want to mention here for read in HDFS. So first of all, multiple readers are allowed to read at the same time, even for the same file. Okay, and the blocks are reading simultaneously, just like writing HDFS. And for each block, we only need to read one replication. One replication of that block. So we always choose the closest data nodes to the client, and this choice is based on the network topology that we have mentioned before. So during reading, we also handles the arrows and the corrupted blocks in HDFS. So during reading, if there found a error while communicating with a data node, and then in this case, the client would or the FS data input stream, the FS data input stream will try the next closest one for that block, but it will also remember the data nodes that have failed. So it will not visit that data node again for the rest of the reading, and it will also report to the name node that there is error or the corrupted blocks. So the name node would write them down and try to fix it, which would be another story. All right, so that's pretty much for today. We have introduced Hadoop, and we have introduced HDFS in details, including the concepts, the architecture, how read and write in HDFS, and a model to help us understand why the replication factor is set to 3. Okay, so that's all for today. Thank you for watching, and see you next time.